Okay, since someone asked this on the JIT, I thought that I would explain this plot a little bit further. So the idea here is that we have two distributions. The first one in gray is my null distribution, which basically is assuming that I have no treatment effect. So this is a null distribution that is centered around 0. And of course, it has some variability, because even if the true effect is 0, as we saw in the previous class, because of sampling variability, I could still get an estimate around here, for instance, but that doesn't mean that the effect is not 0. It's just that there's some variability depending on my sample at hand. This other distribution here is my alternative distribution, okay? My alternative hypothesis. The idea here is that it's centered not around 0, and it's centered around the true value of the effect, which of course I don't know, but I can assume, for instance, it's of course different than 0, and in this case we're assuming that it's greater than 0, so we are assuming a positive effect. Alpha here, or 0.5 alpha in this case, is basically related to the p-value. So remember that the p-value, or the type 1 error, is the probability of rejecting the null hypothesis if the null hypothesis is true, okay? So basically this means that for some reason I got an extreme value, either up here on the distribution or down here on the null distribution. And because I got such an extreme value, and it's very unlikely that just by chance I got that sort of value, I will reject the null hypothesis. However, in this case, it's clear to see that this value still comes from the null hypothesis, so I would be wrongly rejecting the null. Because we're assuming that any extreme value in this case is possible as an alternative hypothesis, I take both the upper tail of the null distribution and the lower tail of the null distribution. That's why I'm considering 0.5 alpha instead of alpha in this case. Usually alpha is considered 5%, that's a typical value. So in this case, this area right here, the purple area, will be 2.5%. Now let's assume that we actually have an effect that's different from 0, okay? And it's basically this distribution here of my alternative hypothesis. If I get an estimate around here, for instance, it means basically that I cannot really distinguish it, whether it comes from an alternative hypothesis or from a null hypothesis in that case. Because I would be in this point of the distribution of the null and in this point of the distribution of the alternative. It's not such an extreme value for the null hypothesis, so I can't reject the null. So basically what this orange region here is telling us is the probability of making a type 2 error. And as we had seen in class, type 2 error is basically the probability, or the probability of making a type 2 error is the probability of rejecting, of not rejecting the null hypothesis, given that the null hypothesis is not true. So again, remember that our estimate is coming in its true value from this alternative distribution. However, because it's around here, for instance, we can't really distinguish it from coming from a null distribution, so we can't reject the null. So this will be my type 2 error in this case. By complementarity, as we saw, power is 1 minus the probability of making a type 2 error. So in this case, everything that's here on this pink side will be the power of my test. So basically what I'm saying is that if I get any sort of estimate that is in this part of the distribution, I will be able to reject the null, again, because I am on the very upper tail of its distribution. And I will be able to reject the null and say that there's actually an effect. As you can see, as the alternative hypothesis shifts to the right, the two means of these distributions will be farther apart, and also it means that this orange area is going to get smaller. Again, which means that the probability of me making a type 2 error is going to get smaller. That's why it's way harder to actually commit a type 2 error for bigger effects. However, for very small effects, where these two distributions are very close together, it's very likely, depending on my sample size, that I actually make a mistake. And for instance, not reject the null hypothesis when I should reject the null hypothesis, given the true values. What my sample size basically does is to reduce the dispersion of these distributions. So if these distributions are tighter, then again, the probability of type 2 error, it's going to be smaller.